general chemistry. So I'm going to talk about mixing liquids and vapor pressures of uh, volatile things. So oops, mixtures of volatile uh, solutes. Let's call it solvents. Volatile substances. Let's hedge our bets here. So what do I mean by a volatile substance? Well, if I had my favorite picture here is, so if I have, let's say, pure A, right? So I'll have a liquid, and I'll have A is a liquid, A is a gas, and there's nothing else in there, okay? So there's no air, I just have this stuff and it's vapor, right? And at equilibrium, I'll have its chemical potential in the liquid, and I'm going to put a star here. This is the notation. This means that it's pure, pure, pure. So there's nothing else in there. So I have pure A in the liquid, and of course that's going to be equal to this standard state plus RT log, and I'll also use this star for the vapor pressure of that pure stuff. Of pure A. You know, and I could, well, let me just leave it like that. But now if I have a mixture, so that could be water, right? And I can now make a mixture. It's only Wednesday, but we start thinking this way if we're early, precocious. I can have a mixture here of A and B. So that could be water and alcohol, for instance. And up here I'll have A and B in the vapor. And so I'll have some proportion of A and B in the liquid, and I'll have some proportion of A and B in the vapor. I could have taken 2 moles of one and 1 mole of the other, and of just the liquids, and put them in there and let it all come to equilibrium, again where there's no air mixed in there. And now I have, they're not pure, right? So I'll have mu A in that liquid, and it's going to be mu A at the standard state plus RT log piece of A over piece of this symbol here, standard pressure, 1 atmosphere typically, right? And we'll have a similar expression for the chemical potential of, there's no subscript here, for B. And that's just what it is. And the thing is, the values are different, because if I have a mixture of these things, then the vapor pressures will be different. I mean, et cetera, et cetera. Now we can rearrange this just to make it a little easier. I can use a different standard state. I could write this as, you know, we're always free to pick our standard state. And picking the separate pure vapor pressures. I mean, and if you want to derive that, you can do some algebra and take these definitions here. Oops, get my flashlight. And this definition, and there's a similar one for pure B and then just rearrange them and get this. Now, okay, so now we go back to Chem 1 and we say, okay, if I have a mixture, so I guess sort of one of the ideas here is, let's not lose sight of the ideas. Let's go back to the pure thing. At equilibrium, the chemical potential in the vapor is equal to the chemical potential in the liquid. Because if they weren't equal, then evaporation would occur or condensation would occur. Because by doing that, I could adjust my pressure, lowering it or raising it so that now everything is happy, right? Goldilocks and the Three Bears, do you still get that read to you? You know what I'm talking about, right? There's three porridges. Does anybody eat porridge? I guess. Okay, so you have porridge that's too hot, porridge that's too cold, and porridge that's just right, right? So that just right situation is when these are equal, okay? Now if I have a mixture, and you know, lurking, I should mention this, lurking behind everything, is that we're talking about ideal gases, okay? So we have ideal gases in the vapor phase. They don't know about the presence of the others. And we're also going to be, this sort of, there's, I guess, some additional assumptions here. We're thinking about ideal solutions. So the solutions don't have things going on. Like if I mix two things and they react with each other, right? If A and B can chemically react, then things are way different. And if they interact strongly, you know, differently in the liquid than they would in the vapor, then things get more interesting. But we're ignoring all the interesting things, and you probably would agree with that. And we're just sort of focusing on just the main idea, the simplest picture of this. But so when I have a mixture, again I have the situation where the chemical potentials of the A's and the A and B and whatever else is in there, in the vapor, I mean in the liquid, is the same as in the vapor. Otherwise things would adjust. Now, if I have, so now we have to add some additional ideas, and you will probably remember. I don't blame you if you don't. And there's always these names associated with these things. But there's something called Raoult's law, however you say it. Back in Nebraska, you know, we never saw anybody with a name like that, right? So the Raoult's law is what we would call it. And do you remember what this is? So if I have my mixture, if I have my liquid, you know, there's A and B in there, and I have XA, which is the number of moles of A divided by the total number of moles of A and B, and XB, which is the moles of B divided by the total number of moles A and B. And these are mole fractions. And if I have my vapor up here, I have a PA and a PB. And down here I have an XA and an XB. And P sub A, and this has to do with the ideal gas. You know, they're just in the liquid. There's just sort of less A than there would be if the whole liquid was A, right? And so the vapor pressure above that is going to be X sub A times what the vapor pressure of A would be if it were pure. So if I had 100% A, there'd be a vapor pressure. If I had 100% B, there'd be a vapor pressure. And the pressures are not going to be the same because A and B are not the same things. They have different properties. But this is an approximation. You know, probably in general chemistry, you talked about reality more than we are in here. There's non-ideal solutions. You'd have deviations from Raoult's law. You probably had to do some problems or something associated with that. I don't know how there's more hours in a day in other classes than we have in here. But if I do this, there's a total pressure, which of course is the sum. You know, what is this? Dalton's law of partial pressures is another name. I didn't write it down, and I certainly don't remember it. If I add these, I get the total pressure. And so I can make a graph of pressure versus mole fraction of A. Let's pick A. And you know, mole fractions go from 0 to 1. And if I have pure A, so if XA is 1, then of course the pressure, let me be consistent with the way I drew this in my notes, or it's going to be a problem. So this is what pure A's mole vapor pressure would be. But if the mole fraction of A is 0, then I have pure B. I'm going to have a point here, which is with the pure vapor pressure of B. Now, if I graph using this equation here, if I graph and just want to know what the partial pressure of A is, it just goes up linearly. So this is P sub A, and it goes from 0 to P sub A star. Of course, I was trying to avoid doing this, but of course I did it, which was to put this right where I'm going to draw something else. So let me draw my lines. Likewise, P sub B, slight non-ideality there. That's supposed to be a straight line. And this is P equals PA plus PB. This is P sub B, and this is P sub A. So you get a picture like that with straight lines, you know. So I've had 2 cups of coffee today, not perfectly straight. You've seen this picture in general chemistry, right? And what that means is if I have the situation at a given temperature, right? I have pure A in a container. It doesn't even matter how much I have, right? As long as the situation is it doesn't all evaporate. So I have an equilibrium at a temperature. I have pure A, liquid and vapor. There's a vapor pressure up here, measured in atmospheres. Do the same thing with B, and there's a higher pressure, because the way I drew this picture, B is more volatile. It prefers to be in the vapor phase, and there's lots of physical reasons why that would be. Maybe A's they interact more strongly, you know. So when they're in a solution, it takes more heat to get them out of there. So they like to hold on to each other in the liquid phase, and they don't tend to be as much in the vapor phase. Whereas the B's may be more, you know, they don't like each other so much, so they prefer to move to Montana, where the density is lower. But that total pressure, then, as I vary this mixture, as I vary the recipe of my cocktail, will be that total pressure line. And you probably spent time in general chemistry looking at pictures where these lines bend and stuff, and then you talk about the hydrogen bonding or this and that or whatever is causing things to be a little not ideal. Okay, so we can go back here. So using Raoult's law and using our expressions here, right, we can very quickly then write down expressions for my chemical potentials. In terms of these mole fractions, because the PA star and the X times PA star ratio cancels out and gives me this. Okay. So that, I mean, there you have it. That gives you how, I have a total number of moles of A and B. I can get the mole fractions. I mix them together without any additional anything in it. No solutes, no extra air in the vapor, because that would then lower the vapor pressures, right? So if I put air in there, what would happen? Let's just think. Would more would more stuff come in? I think it would drive it back into the solution. It would lower the mole fraction of those things. All right, so let's look at now the thermodynamics of mixing liquids. And if I work that out, you know, I have an initial, and let's say, you know, A and B. So we're mixing two things, a simple cocktail, right? So initial Gibbs free energy G0 is, oops. So, you know, I have a bottle of A and I have a bottle of B, and I have a shot glass or whatever, something to measure how much I add of A and B. And the recipe calls for N sub A moles of A, and then N sub B moles of B. And so still in the way I would think about it, it's still in the bottles. There is like a subset of the bottle that's going to leave the bottle and go into my mixing thing. So N sub A moles I'm going to take out of a bottle, N sub B moles of B I'm going to take out of the other bottle. And so the chemical potential of those things that are destined to be mixed, or the Gibbs free energy, is this, because A and B are still pure, right? So they have their pure chemical potentials, and in the again, forget about the air. In the space above the bottle, there's a vapor of A and a vapor of B. Those vapor pressures are the pure vapor pressures. But then after I mix them, so the final value, I'm not going to write Gibbs free energy. I'm going to have N sub A, then I'm going to have mu sub A star plus RT log X sub A, right? Plus N sub B mu sub B star plus RT log X sub B. Because now they're not pure, and they're mixed, and there's this composite vapor above them. And if I work out delta G, and I can say of the mixology, just subtracting, I get N sub A RT log X sub A plus N sub B RT log X sub B. But we can do the same thing as we did with the gases. We can write this as N, where N is N sub A plus N sub B RT, and then put in here X sub A log X sub A plus X sub B log X sub B. So it's the same as if we mixed, for these ideal solutions, the free energy of mixing them is the same thing as mixing their vapors, if you will. So there's this sort of a logical connection between what's going on in a liquid. Well, the liquid is in equilibrium with the vapors, and the vapors are mixed. And when I mix the vapors, their chemical potentials change, so the liquid chemical potentials change along with that. Okay, so there we go. Now we can deconstruct this and say what are we really saying about this solution? So this ideal solution. Properties. We can sort of infer this. so we saw previously, the delta S of mixing. We saw previously, and then assuming this sort of connection between the gases and the liquids. So, and remember the minus signs, always, beware the minus signs. The wizard said, or the caterpillar on a mushroom said to you. And that minus sign may look like delta S of mix is negative, but no, not the case, because all these logarithms of numbers less than 1, they're all negative. So that's positive, right? The delta S of mixing is in fact positive. And my delta G of mix is going to be delta H of mix minus T delta S of mix, just general chemistry. And so I see one of the hiding assumptions here is that delta H of mixing is 0. And that means, what does that mean? It doesn't mean that that there's no interactions between the solvents, right? Things are in the solution phase, and they interact with each other. But what this says is that A and A and A and B interactions can you read that? The answer is no, so you don't have to answer, because I can't either. And this is sort of just a comment in passing, because we're not really using the fact that they're even molecules so much in this way of teaching P-Chem, right? If thermo could be last, then we could be using the Schrodinger equation to talk about things. But these interactions are the same. So the A and A interactions are the same as the A and the B. If they were different, like let's say AB interacted much more favorably than A and then B and B. If I mix them together, then A and B would be really happy, and delta H would be negative, right? Because interactions would occur, and heat would result in go into surroundings and raise the entropy of the universe. Don't forget that entropy of the universe is always leaking, or lurking, not leaking, lurking behind everything we do. But for this, if delta H of the mixing is 0, then that's what it says. That's what it's saying. Okay, and you probably did some problems along these lines in general chemistry too. There are these things called colligative properties. Remember this? What are a couple of colligative properties? This could be on the MCAT. Do people still take MCATs? Or have they banished them too? Okay, so like freezing point depression, boiling point elevation. And so what this is I have it's related to what we just talked about, but let's say I have, pure A. And so I have A gas and A liquid, and they're at equilibrium, okay? And then I imagine I throw in some, let's say this is sucrose, something like that. So now we have when we have distinctions, we have to come up with labels. So here A is now the solvent, and let's say that's B. B is the solute, and here now B is non-volatile. So what does non-volatile mean? I mean, when it comes to selecting roommates, it's a very desirable property, because you don't want every time your cat, does something that it's not supposed to do, you don't want your roommate getting all upset. Volatile means that you're very emotional. Non-volatile, you're very peaceful. But in this case, it means that it has a very low vapor pressure. So essentially zero. So there's none of that B in the vapor phase. It's all in the liquid phase. So if you take pure water and you measure its freezing point and boiling point, and then you put some salt in it, let's say, it's better to put something that is like sugar, that doesn't interact strongly. But like if you put what happens if you have, this is a bad question to ask Southern Californians, but if you're living in Nebraska, okay, and you walk out of your house, and this happened to me a lot, okay, I would end up very quickly sitting on the ground. I was standing and then I was sitting, and I didn't do that deliberately. The campus got very icy, so when you're walking on the sidewalks, very icy, very slippery. And so you'd slip. So if you put salt on ice, what happens? Melts. Why? Well, having salt, if you have any liquid with the salt in it, the freezing point is lower. Okay. So, and it's very, you just dump it. You don't put a sprinkle of salt, right? You just dump it. So other things are at work, but basically, if you have something dissolved in the liquid phase, then the freezing point, like freezing that liquid to a solid, you have to get it to a lower temperature, okay? And likewise, if I have something dissolved in a liquid and I want to boil it, I have to crank up the temperature even higher to get it into the vapor phase. And so the thing that's different, and this is just the idea. So if I put a solute in liquid, it goes into the liquid, right? There's some solubility. Now, when I freeze that liquid, like if I have seawater and I freeze it, so I have an iceberg. Okay, is that iceberg salty? No. The salt basically is not in the lattice of the crystal. It doesn't want to be there. That'd be very thermodynamically unstable, having this intruder messing up the very organized structure. So, like the solid is pure, but the liquid has the thing in it. The vapor phase is pure if it's non-volatile. Okay. If it's volatile, like what we just talked about before, this is not relevant. But if it's non-volatile, it preferentially stays in the liquid. And so the liquid has something in it that is changing the thermodynamic desirability of molecules being in the liquid. Okay, and so we want to understand that. And of course, we're going to understand that. And the difference between this class and there's some value of the upper division class, I suppose, is we have our mathematical formulas to use. So let S equal solvent. So that's the A in my example, right? So the solvent's chemical potential is the pure stuff, right? Plus RT log of X of the solvent. So pure, X of solvent equals 1, but in a solution with B added, the X of the solvent is less than 1. So the chemical potential of being, this formula tells me the chemical potential of being in liquid phase has gone down a little bit, right? And if a chemical potential goes down, then there's a bias towards being in that phase. We can draw our picture. Remember, we have this graph of mu as a function of t. Let me draw like this. So this is pure liquid, and this is the pure vapor, and this one's the pure solid, right? Now, I add some solutes, and I go up here and I look at this equation. And this equation's true for the gas, okay? So you have to take my word, I suppose. Well, it's true for the liquid in equilibrium with the gas. So we'll just use it. For the liquid, I add this. So I add solute to the system. What happens to all these chemical potentials? Well, the solid and the vapor, they don't change because they're still pure. But this, this is the solution value. So what has happened? It's gone down. And this was the freezing point, right, of the pure, and this was the boiling point. I'll put a star, that's a good notation. The star means the pure stuff, and without the star means the stuff that's not pure. And so you can see there's an elevation of boiling, and there's a depression. Depression here means decrease, right? And which one's bigger? So, like, you know, if I have some water and I put some sugar in it, and I go measure the freezing point depression, and I measure the boiling point elevation, which one's bigger by the graph? Right, delta TF is bigger, let's say, absolute value. Bigger change. And that's because the slopes are very similar. You know, and you know, there's some formulas with the entropy, delta S of the, you know, there's all this that can be done. And then, you know, there's a lot of problems that you can do and probably did do, right? I mean, calculate, you know, here's a bunch, and there's more we could talk about, but that's all I want to really say about it, because I want to move on to more interesting things. We're supposed to do kinetics and everything. I mean, I don't have any illusions about covering what the class is supposed to cover, but I do want to make some progress. So that's all I'm going to say about mixology, mixing liquids. Just a few ideas. I'll give you some problems so you can have some idea as to what you're supposed to have gotten out of this, other than just more convictions about my poor handwriting. But now, okay, this is not physics, right? This is not the physics. It's not a chemical physics class. It's physical chemistry. So that's really the difference, right? In my mind. So we're going to talk about chemical reactions now. And in particular, you know, we'll focus on chemical equilibria because, you know, chemists, equilibrium is like, okay, I mix some stuff, I mix some reactants, what am I going to get out of it, right? Well, there's all the questions of yield, which are not related really to thermodynamics. They are, but, you know, many other factors come into play when you're actually in the laboratory with the fire extinguisher in one hand and, you know, some whatever, trying to do a chemical reaction. But But equilibrium is when the reaction is just done and we have now a mixture of reactants and products. Of course, the interesting thing is when there's a chemical process, like your body, metabolism and making ATP and using ATP. So there's all the non-equilibrium interesting things, like the electron transfer, all those things. But mainly we'll talk about equilibrium. So trying to decide what you have in a reaction after something happens and it all settles down. So a chemical reaction, someone like me, is an equation, right? So like we have A, B, C. These are the stoichiometric coefficients. They have some fancy name like that. And A and B and C, these capital letters, are just the names of the stuff. So for instance, we'd have like 2H2 as a gas plus O2 as a gas, giving me 2H2O as a gas. And those small letters A, B, and C, they're all positive, right? So we have 2 moles of H2 and 1 mole of O2, and then if the reaction went all the way to completion, we'd have 2 moles of water. But but we have a little bit of H2 and O2 left. It doesn't all go to water. How do we figure out what those proportions are at the end? So it's better to use Greek letters. Okay, it's a capital G, because that makes us look more intelligent, right? So we'll have the nu sub j's, which are the stoichiometric, which are signed stoichiometric coefficients. Gesundheit. So they're positive for products, and they're negative for reactants. So I can write my chemical reaction. So this is my chemical reaction. Who would have thunk it, right? So instead of writing this out, I could write it like that. So I could put I could have 2H2 or 2H2O minus 2H2 minus O2 equals 0. And I could read off from that all these news. So that's just a convenient way of writing it. And so if we're normal chemists and Tp are constant, so we're in the lab, open containers, then I have G, which of course depends on, and let's let this be R components again. So R equals the total number of chemical species. And so let's go back to this reaction. I'll just add it here. So nu H2 is minus 2, nu O2 is minus 1, nu H2O is 2, right? And R equals 3. So there you go for that one. But J is labeling these different species. And so I have a Gibbs free energy. And I can find dG, and it's just going to be the sum of J from 1 to R, mu sub J dN sub J, because there's also minus S dt plus V dP, but like I said, these are constants. You could devise some problems that are more unpleasant where you could change those things, but let's just stick with this here. And remember, mu sub j is partial g, partial n sub j, t, p, and n sub k not equal to j, all constant. Now, I could come up with some way whereby I'm adding moles of this and that and seeing what happened, moving moles from a, you could almost have like a mixing kind of a thing going on here. But if it's a chemical reaction, you know, the ends are not like change of the n sub j's are not free, right? They're constrained by the stoichiometry. Meaning that like there's one knob that you can turn that takes you from reactants to products, and they call this thing almost well, the letter C, that's the Greek letter C, and we can call it the degree of advancement. Some people call it that. Graduate students all have a degree of advancement too, right? And it goes from 0 to, I don't know, how many years does it take to get a PhD, you know? But that's, you know, they advance to candidacy after a year and a half or so. Or we could call this the extent of reaction. And these ends, the ends sub j, are linked to that single variable by their stoichiometry. So dn sub j is nu sub j by d xc. So like if xc goes from 0 to 1, right, then what happens is all the products increase by n sub j, and all the reactants decrease by n sub j. Okay, according to this expression. So I can write my dg as the sum of j, mu sub j, nu sub j, dn, dxc. Right, so there's my dn sub j. But I can sort of factor out this whole thing. And we can give this a name, right? And this quantity, if you look at that, okay, so I took, and again, one can have a lot of fun with multivariate calculus, okay, in general, but we'll just notice, I guess, the obvious. So G is a function of T and P and N1, N2 up to N sub R. But it's a sort of an illusion that you can, in this situation, the N1s and N2s up to N sub R, they're not independent. They all depend on a single variable, which is Xc, okay? And so I can take the partial derivative of G with respect to Xc, and I can hold T and P constant because those are the only other actual variables. And that is what this quantity is, because dg is going to be partial C dg at constant T and P, right? And I could write dg as minus sdt plus vdp plus that term, but I'm not going to bother to do that. That's that quantity, and it's defined. And so delta sub r of g, I'll probably forget to put the r before the g, but this is the reaction Gibbs free energy. okay? Reaction gives free energy. Let's see if so I can, you know, I can draw a picture. I can plot G as a function, and let's say, oops. And I'm not going to, you know, I'm not going to say, you know, Xi could be whatever, you know, like I said, Xi goes from 0 to 1, then all the mole numbers change up or down by their stoichiometry. But you know, maybe, you know, it depends on how much initially you have, how far G can go. So I'm just going to draw it here without giving the limits. But this is what happens. It looks something like this. So this is G as a function of T, P, and Xi, and T and P are constant. And so there's a slope here, right? Delta reaction of G is less than 0. Over here, delta reaction of G is greater than 0. And there's some point, I'll call it Xi sub E. Right there, delta reaction of G is equal to 0. And that's typically what this curve is going to look like. But the punchline will have to wait until Friday because we're now pretty much out of time. So I'm going to stop, and you're gonna leave. I'll see you on Friday. But I'll send you some stuff in the meantime, and I'll be up here if you have any questions.